matrix multiplication is where things get fun. And so it's very similar. So one of the first videos this week, I reminded you, or we talked a little bit about how to multiply a matrix and a vector. Right, so to multiply a matrix and a vector, so say I had A, B, C, D, and x1, x2, right? All I did was took this row times this column and the corresponding entries, and then I added them, right? So we had A x1 plus B x2, and in the bottom we'd end up with C x1 plus D x2, right? And again, this is a vector. Well, if we think about our matrix being a bunch of column vectors that are sort of squished together in the same matrix, then the idea of matrix multiplication follows the exact same principle as matrix and vector multiplication. But first we actually need to worry about the size of the vectors. So because we're matching up rows and columns, we have to make sure that the sizes match up. Now, unlike addition, they don't have to be the exact same size. However, the number of rows in the first matrix needs to equal the number of columns in the second matrix, right? So here I have 2 rows and here I have 2 columns. Right, so just like with our vector multiplication, we had to make sure that the number of entries in our vector was the same as the number of entries in our matrix, right? So this is a 2 by 2 matrix. This is a 2 by 1 vector, right? I have 2 rows, 1 column, and you'll notice these numbers are the same, right? 2 equals 2. So for any size matrix, if I have some m by n matrix, I can multiply that by some n by p matrix, right? So notice these are the same. And the result is actually going to give me a matrix of the size m by p. So these are going to give us our new matrix size. Which kind of makes sense if you think about it, right? So the number of rows, so that's how many times I'm going to, that's how many rows I'm going to end up with in my new matrix. And the number of columns here is the number of columns I'm going to end up with in my new matrix. So the row column rule, so we're not even bother with doing the whole, we could do this as a bunch of matrices or as a bunch of vectors, do, vector addition and blah, blah, blah. We'd be here all day. So we're just going to skip straight to the fun part, which is our algorithm here. So our algorithm says that if I have 2 matrices that we can actually multiply. So here you'll see I have a 2 by 3 matrix. Here I have a 3 by 2 matrix. These 2 entries are the same, and my result is going to be a 2 by 2 matrix. To get this first spot, so the first position, so I'm going to actually separate this into 4 pieces so we can see there's, so to get my first row, first column entry, so my A11 entry, I'm going to take the first row of A and the first column of A, and I'm going to multiply corresponding entries, and then I'm going to add them together. So that means that I'm going to take A times G, I'm going to take B times K, and I'm going to take C times O, and I'm going to add all those products together. So seems like a lot, but it actually goes a lot faster than you might think. So to get my first row, second column position, so my A12 position, right, that's this guy here, I'm going to take my first row and my second column. Now, you'll kind of notice, if I were to superimpose these things on top of each other, aside from the fact that the number of things don't match up, you'll kind of see where they would intersect with each other would be sort of in this position. And where the first ones would intersect with each other would be in that position. That's kind of how I think about where to put these things when I need to put them somewhere. I don't know if that helps anybody, but maybe. All right, so we're going to do A times H plus B times L plus C times P, and I just picked up random letters here. And then again, so now to get our bottom row of our new matrix, we're going to go to the bottom row. Ooh, boy, that was not the way I meant to do that. The bottom row of our A matrix. And then we're going to go back to the first column in our B matrix to give us DG plus EK plus FO. All right. And last but certainly not least, we need a brand new color. How about purple? Purple's fun. So now we're going to go back to our bottom row, second column, and we get DH plus EL plus FP. All right, so we're going to do a bunch of these as an example. What I'm going to do is I'm going to let you do the multiplication. We're going to come back. But before we actually do the multiplication, what I want to do is I want to actually sit down, or we want to define the sizes of these things to even see if this is possible, right? So the first one we're going to find is AB. So for AB, we have A is a 2 by 3 matrix. B is a 3 by 3 matrix. And it turns out that our rows, that those numbers match. And so our resulting matrix is going to be a 2 by 3 matrix. So that kind of helps us out in terms of like making sure we have all of the right number of entries. So that means that AB is going to equal some 2 by 3 matrix. So I'm going to have 2 rows, 3 columns. So if that helps you, 1, 2, 1, 2, 3, if that helps you keep track of things. If not, just totally ignore me. I can erase those and just, they never happened. All right, so pause the video, try the multiplication on your own, come back, see how you did. How'd you do? Hopefully you did all right. Hopefully I did all right. It is entirely 100% possible that I made an arithmetic mistake. So if you catch it, call me out on it. Love it. All right, let's take a look at the next one. So CA. All right, so this time, so C is a 2 by 2 matrix. A is a 2 by 3 matrix. We have a lovely set of coconuts here. And by that, I mean those match. So we're going to end up with a 2 by 3 matrix again. So give that a shot. Tell me what CA is. And come on back. Or pause. Try it out. Come back. See how you did. How'd you do? Spectacular. Wonderful. How did I do? I guess it's more of a test of did I do it correctly? You know, these things happen. Okay. So let's move on, shall we? All right. AC. Let's see if we can do that. So A is a 2 by 3. C is a 2 by 2. Oh, man. Those are not the same. So this is undefined. Look at that. Multiplication just got so much easier because half the time it doesn't work. All right. It is late, and I am a little cracked up. All right, so we did AB, we did CA, we did AC. How about BA? What's going on there? All right, so BA, that's a 3 by 3 matrix and a 2 by 3 matrix. And again, ooh, that's not the same. So this is still undefined. Ooh, and that's curious. Look at that. So AB and BA. We're going to come back to this, and we're going to talk about this in a minute. But keep this in mind. Think about what just happened there. And hold on to that thought. We'll come back and address that in a minute. All right, so BA doesn't work. How about BC? I have a hunch. BC is probably not going to work either. Oh, hey, we got a 3 by 3 and a 2 by 2. There is not a whole lot that matches that in any way, shape, or form. So, again, we are undefined. Yay! Okay, that's it for our example. So, keeping this in mind, let's go talk about our properties of matrix multiplication and what we can do with these. We saw that if I took A times B, I actually had a matrix, but if I took B times A, I didn't necessarily have a matrix, right? It was undefined in this case. So, matrix multiplication is really interesting. So we're going to assume that A is an n by n matrix and that our matrices B and C in any case are either the appropriate size for multiplication or the appropriate size for addition and subtraction. So as long as all of our ducks are in a row, then these properties hold. So the first property says that A times the product of BC is equivalent to the product of AB times C. So now notice the order that these things are in. So one nice thing here is that this confirms that matrix multiplication is associative. So our multiplication is associative. And the order is really important. Right, so I would have to do B times C first and then times A. And I have to put the A matrix in front of BC. So I can't do BC times A. If I do BC times A, that's a whole different matrix than A times BC. So the order is really important that we write these things in. Okay. If I take A times B, or A times the sum of B plus C, I can distribute this. However, again, notice where A is. A is in front of the B and the C. This is actually called a left distributive property. And the next one says, notice where the A is here. So the A is after the sum. I can still distribute, but this distribution is called a right distribution. Right distribution. Like the direction, not the correctness. All right, scalars. Notice where this scalar is. So I could take the product of A and B, and then I could scale it. Or I could scale A and then multiply it times B. Or I could scale B and then multiply it times A, but notice where A is again. So position, position, position. It's all about that position. Where is our matrix? The last one says that if I take, and you'll notice here that this M and this N change position, and that is entirely because if A is not a square matrix, if A is M by N, then in order to multiply I times A, so if I is an M by M matrix, then I have to multiply it in the front of A. But if I is an N by N matrix, then I can only multiply it after A. Hopefully that makes sense, right? Because I can do an M by M times an M by N, but I can't do an N by N times an M by N. Hopefully that makes sense. I'd have to reverse the order. I'd have to switch those in order to do that multiplication.
Oh, now we're working. Slight pause, change of location. So now we come to the actual warnings about multiplication and where multiplication becomes really, really interesting with matrices. So the first thing that's interesting, and we sort of saw this in that example that we just did, the same size. And even if it is possible to do both A times B and B times A, there is no guarantee that those two things are going to be equal, right? So essentially what this says is that multiplication is not commutative, right? So addition of matrices is commutative, but multiplication of matrices is not commutative. So it doesn't matter who the order is really, really, really important. So remember when I said position is really important for our matrix operations? That's sort of what I mean here. So order is important. Where the actual matrix sits in the equation is really important. And yeah, now some other rules that don't hold. The cancellation laws of algebra don't hold for matrix multiplication because there's so many moving parts and weird things going on here, and the multiplication is not as straightforward as like 2 times 3 or 3 times 2. There's a little bit more to it. So just because A times B equals A times C, that does not actually imply that B equals C. So there may or may not be an example in the practices, but it might be of something else. So just because, and part of this also exists because there is no such thing as division in matrix algebra. So division doesn't exist. The last one says that if my product AB results in the 0 matrix, so A times B equals 0, I cannot actually conclude that either A or B is equal to 0. So I can't assume that, right? Because it is entirely possible that when I multiply these things together, that the pieces in the columns and the rows will multiply together and their sum is going to come out to be 0. So A and B could both have non-zero entries, and the result of their product could result in the 0 matrix. So some things to be cautious of, and again, just kind of keep in the back of your mind that matrix algebra does not work the same way that normal algebra does. So there are some key things we have to keep in mind. All right, the last thing we're going to talk about in this section is the transpose of a matrix. And the transpose of a matrix, straight simple. All we're going to do is flip the rows and the columns. So the first row becomes the first column, second row becomes the second column, so on and so forth. That's it. So if it's an m by n matrix, then it becomes an n by m matrix. So here we go. We're going to find the transpose. Now we denote this by A with a little t up there. And that's what that means. So it's kind of like an exponent, but it's not an exponent, it's just a notation. So our transpose of A here, what we're going to do, so our first row becomes our first column. So AB and then CD here. There we go. So it's kind of like really the only thing that happens in a 2 by 2 matrix is those two positions switch places. For B, because this is a 3 by 2 matrix, our transpose of B is going to be a 2 by 3 matrix. So our first row becomes our first column, and so on and so forth. So 1, -3, 0, 4. And then for C, again, this is a 2 by 4 matrix. So our transpose of C is a 4 by 2 matrix. So we have, what did I say? 1, 1, 1, 1, -3, 5, -2, 7. Can't get any simpler than that. Transpose, probably the easiest operation that we can do. Some final notes on the transpose. There are a couple of properties. You're going to notice some of these are kind of similar to other properties we've looked at. Some are a little bit different. So the first one says that if I take the transpose of the transpose, I get back to what I started with, which should make sense, right? Because if I just reversed the rows and the columns, if I go back, it's essentially going backwards. If I take the sum of 2 and then I transpose it, it's the same as taking the transposes and then summing them. Same thing if I take a scalar times my matrix and then I transpose it, it's the same thing as taking the transpose and multiplying that by a scalar. And then this last one, notice the order over here. So if I have A times B, so if I have a product of 2 matrices and I take their transpose, it is the same as taking the transpose of each individually and then multiplying, but the order is very important here. So it has to be that our B would come first and then our A would come second in our multiplication order for our transpose. And the reason that works, or the reason that kind of has to be, right, if you think about this, so if we're going to multiply A times B, so let's just for funsies, let's say that A is a 2 by 3 matrix and B is a 3 by, I don't know, 7 matrix. We're having fun here, right? That would mean the transpose of A is a 3 by 2 matrix, and the transpose of B is a 7 by 3 matrix, right? If you think about the product of A and B, so AB as a matrix is a 2 by 7 matrix. And then if I took the product of, and notice I can't actually take the product of A, so A transpose B transpose is undefined in this case, right? Doesn't work. But if I flip that and I do B transpose times A transpose, I get a 7 by 2 matrix. And if I take the transpose of this, I get a 7 by 2 matrix, so those are the same. So hopefully that kind of makes sense. All right, that is it on our matrix operations. We're going to talk about one more special kind of operation in the next video, and then we are getting close to the end here, folks.